All right, so now we're going to discuss the concept of stable matchings. So this is for something that pops up when you have like jobs and applicants. And so each job has a certain number of people who had applied, and the committee had ranked those candidates. And likewise, each candidate has a ranking about for the jobs they applied for, which ones they prefer to which ones they want the least. Or you have potential roommates who have ranked all their possible options. And so in other words, you have a graph G where for every vertex you have a total order on the neighborhood of that vertex. In other words, it's the statement of preferences for that person of which of the partners it wants to be matched to the most. And so what we want to find is what we're going to call a happy matching. So what we want to do is you want to find a matching so that as many people are matched as possible, but with the property that none of the non-matched edges is preferable. So given a non-matched edge, it must be the case that U prefers the person they're currently matched with, or V prefers the person they're currently matched with. So in other words, given a matching and these order of preferences, we're going to say the matching is unstable if there exists an edge with the property that both endpoints are unmatched, because then there's a larger matching we could make. Or U or V is unmatched, the other vertex is matched to some W, and V prefers U to W, because then that's this setup here. V is a match to W and there's U, but V would actually prefer U, because then V should switch. And the same happens in the third case. You have a potential pairing, an edge, UV. They are both matched. U is matched to W, V is matched to Z, but they would prefer each other. Because then the point is then both these could break off their current matchings and match, and they'd be happier together. If M is not unstable, then we call it a stable matching. So stable matching is one where in every unmatched edge, one of the two endpoints prefers their current matched partner. So here's our theorem. Suppose you've got a bipartite graph, and you have total orders on the neighborhood of each vertex. Then G actually has a stable matching. So here I'm going to use the notion or terminology of jobs and candidates. So the point is a bunch of people had applied to a bunch of jobs. Stable matching would correspond to people getting hired, and has the property that for any job application between a candidate and a specific job, it must be the case that either you got a job or V hired someone. And in those cases, either there's a preference, so either V prefers the candidate they ended up hiring, or you have to have the case that you got a job somewhere else and they prefer this other job. So we're going to do this proof in stages. So there's some setting up we're going to have to do. We're going to let A and B be the partition by partition. And I'm going to use M of A, M from A to B, and M from B to A to be functions that correspond to the matchings. The idea is supposed to be if U is matched to W, then I define M of U to be W and M of W to be U. And when vertices are not matched, I'm going to let the other endpoint be negative infinity. And so we're going to start by making the matched pair of every vertex be negative infinity. This negative infinity is a new vertex that's not in your original vertex set, and the whole point is that for any of these orders, negative infinity is less than everything else. So this is a condition we're adding to make the proof go easier, because the whole point is once a potential pairing is given, there's going to be a preference. A person's going to prefer a job to unemployment, and a job is going to prefer hiring one of the candidates to not hiring anybody at all. Now here's our other setup. We're going to create these sets, B of V. So for every vertex in A, we're going to let B of V be the neighborhood of V. And then for every vertex in B, we're going to let A of U be empty. I'm going to let A be considered the set of jobs. And so what B of V is going to represent for every job is the set of candidates that the job has not already rejected outright. And likewise, A of U is going to be the set of job offers vertex U gets at a certain point in the process. So then here comes the algorithm. This is also known as the Gale-Shapley algorithm. As long as there is a job that has at least one potential candidate, so the union of the BVs is not empty, then we do the following setup. So this is the first phase. For each job that has yet to find a preferred candidate, or currently does not have a preferred candidate, and for which the list of potential candidates is still not empty, what the job does is it takes the best candidate in its list, so the maximum with respect to the order for V. It removes that candidate from the list, and then it sends that candidate a job offer. So it submits that job to the list of offers that candidate has received so far. So you do this for every job that doesn't currently have a candidate and still has options left. Okay, so after all that is done, then you look at the candidates. So for each candidate that currently has at least one job offer, the candidate takes their favorite or their top choice among the offers they've received. They compare that to any current job they have tentatively accepted. And if they prefer the new offer to anything they've currently accepted, then they now accept the new job down here. Of course, if they currently had a preferred job that they've already accepted on a previous round, so M of U is not negative infinity, we're going to remove that job. So this argument steps are here for the situation where you already previously had accepted a job and now a so-called better job has become available. Then the idea is that they want to go back to the previous job and tell them, no thanks, I've changed my mind. And that's what this setup is doing. It's now saying that M of W no longer has a candidate. And then they now accept this new preferred job, and this new preferred job has accepted them, so you now have a new matched edge. And then, of course, we reset the set of offers vertex U has received to the empty set, because now vertex U has temporarily accepted a preferred job. And then we define our matching after this stage to be the set of VMV, where V was matched. So the pairs of jobs and their candidate who had tentatively accepted the position. And I say tentatively because of the fact that later rounds in the algorithm could run into this situation where one of the people who has tentatively accepted a job changes their mind. And so this algorithm continues until this while loop is no longer true, which means that every job has run out of potential candidates. Now, reading this setup, I see one little issue I've forgotten to take care of is that once a job has hired a potential candidate temporarily, we run into the issue that their B set no longer changes. So I ought to say here that there exists a V in A with M of V equal to negative infinity. So in other words, as long as there's a job that hasn't been filled yet, and that job still has a potential candidate, then we should keep going. So then we hit the end of this while loop if that no longer happens, which means that any job that hasn't been filled yet has run out of candidates. So now let's run the algorithm. So here's a bipartite graph. We're going to assume every person has applied to every job. And we're going to assume somehow that each job has ranked the candidates in the same order. So C is best and A is worst. It turns out A and B have the exact same linear order. They read from right to left. They prefer job D most and job F least. But then person C does things in the opposite order. So on the first round, each of my jobs has a possible candidate they could hire, literally any of the three. And so they each prefer sending the offer to their favorite candidate. In this case, it's all the same person. So the same person receives all three offers. So A of C is D, E, and F. According to this linear order, vertex C is going to accept the job offer from F first. And so we now add that edge to the matching, and we've removed vertex C from the possible list of candidates from each vertex. All right, so then each of the jobs that currently hasn't hired someone sends out an offer to their favorite person on their list. So they've removed C, so their favorite person is now B. B ends up receiving a job offer from both D and F. However, according to the linear order on B, job D is preferable to job F, so they're going to accept job D. And so now that is what we have happen. And so again, candidate B has been removed from consideration. And then finally, job E that hasn't hired anyone is going to send a job offer to A. And that's the one that accepts. Note in this weird situation, E ends up hiring the person that was the least on their list. But when you look at, say, the other possible choices, like E could have hired B, but the issue is B prefers job D to E. And so we see that this is stable in that sense. It is not an unstable edge. And likewise, if we look at EC, C prefers F to E. And so again, this is not an unstable edge. So you can check all of them, and you'll see that they're all stable edges, and so this really is a stable matching. You also see that this matching happens to match every job and candidate, so every candidate actually gets hired somewhere. And this is actually something Gale and Shapley originally proved, that if you're working with a complete bipartite graph where you have n vertices on both sides of the bipartition, then the stable matching you get actually does match every vertex in one set to a vertex in the other. So I need to claim that the matching we get when the algorithm terminates is a stable matching. So one thing worth noting is that after each step, after the first round, for every vertex, every job, there's at most one candidate they sent a job offer to. And likewise, for each candidate, there's at most one job they accept, either one that they had accepted previously or the updated. And so as a result, this guarantees that after each step, the set M is in fact a matching, because the only way to have this situation would be for one candidate to have accepted two jobs at the same time, and the other situation is for a job to have sent an offer to two candidates at the same time. And that's excluded by how the algorithm works. So this really is a matching. So we need to show that it is stable. So let's take an edge that's not in the matching, and we're going to suppose for now that U is unmatched. And so using the language of jobs and candidates, we're assuming candidate U did not get a job. And then we just point out, suppose that U was the top candidate for some job V at some point. Then based on how our algorithm works, job V would have sent U an offer. So at that point, A of U would be non-empty. And because of how our algorithm works, since there would have been a point where U had at least one job offer, U would have accepted the best job that they are offered. And so in particular, M of U can't be negative infinity after that step, which is a contradiction to the claim that U is unmatched. And so that means U was never the top candidate. And so if U was never a top candidate after every point in the process, then that means that job V must have contained someone better. So it's clear that since you applied to job V, you was always a candidate. And so it must have been the case that at some point in the process, V had hired someone. We'll call it W for now. And V preferred W to U. Now, the first conclusion you could draw is that then V must be matched to this W. It's possible, based on how the algorithm works, that later V matched to something else. So to make this argument precise, you let W be the last vertex at which the value of M of V changed. All right, so that covers case 1. If U remained unemployed, then for every job they had applied to, the job had accepted someone else that they thought was a better candidate. So let's look at case 2. U managed to get matched to a different job. If U actually prefers that job to the job V, then we're done, because that means we have a stable edge. So in other words, we're going to suppose that U got job Z, but U preferred job V. Worth noting that if U was offered job V at any step in the process, then U would have accepted that job. Or if it didn't, it's because U accepted a job it preferred to V. So in particular, the fact that M of U did not end up being V means at some point U accepted a job that it preferred to V. And since it accepted a job that it preferred to V, we see that it would never switch to job Z. And so in particular, we can conclude that U never received a job offer from V after any step. Which means, as argued before, that means that job V must have accepted a candidate the company preferred to U after some step. So I will point out this Gale-Shapley algorithm and other such algorithms have actually been used in various industries. Like it's been used to assign rabbis to congregations in certain branches of Judaism after they finish their training. Or it's students who've gone to medical school. This process has sometimes been used to assign their first residency to a given hospital. And a lot of research has gone into what happens comparing the results if you switch the roles of A and B. So I described the process with the idea that companies first send offers to the preferred choices, and then the candidates decide, and you keep iterating this process. Another option would be if you started with the candidates first, and they send an offer to their first choice of company, and then the company look at the potential offers and then decide. And these two approaches do not give the same exact stable matching, it turns out, in general. And sometimes it turns out the stable matching is more optimum for whichever side starts the process.